Okay, IB topic 6, kinetics, the second portion of this unit. Kinetics, the study of the rates at which chemical reactions take place. Some reactions take place, right before your eyes immediately. Some take place over a very, very long period of time. The rate of a reaction, an increase in products or decrease in reactants per unit of time. In other words, we could look at the rate at which something is being used up, consumed, or we could look at the rate at which something is being produced. Most commonly reported as a change in concentration per unit of time. So let's look at an example of that. So this reaction, magnesium with hydrochloric acid, producing hydrogen gas and magnesium chloride. So what we're going to do is look at the concentration of the hydrochloric acid. Remember, brackets is a way of representing concentration. So as this reaction proceeds, as time goes by, the amount of hydrochloric acid, the concentration of hydrochloric acid, will go down and down and down as the hydrochloric acid is being produced. So how can we plot, or how can we use this plot to determine the rate at which the hydrochloric acid is being produced? Well, we can just stop it at any given time. So let's say at time t here. And if we draw a line that's tangent to the curve, and then determine what the rise over run is, well, that would be the rate of the reaction. The slope, rise over run, is the rate. And so that would be a change in concentration. So this is a change in concentration over a change in time. So moles per liter per unit of time. So that would be our rate of reaction. Now that can be rewritten as moles per liter seconds, and that's how we would say it, moles per liter seconds. That little dot there, often you'll see a little dot put between units. It's just to help distinguish between them, that they're not one unit. If it was LS, it would kind of look like it was one unit, but this is liters per seconds. Now in your textbook, it would say moles per cubic decimeters per second. Remember, negative exponent just means it's in the denominator. A cubic decimeter is the same thing as a liter. In our next unit, we'll visit these units in more detail. I just thought I'd mention that in passing. For this unit, we'll be using just moles per liter seconds. A balanced chemical equation can be used to compare the reaction rates between reactants and products. So let's look at the same reaction that we just looked at. And let's say that we know the rate that the rate that the hydrochloric acid is being consumed, that it's consumed at the rate of 0.30 moles per liter seconds. And we want to know at what rate is the magnesium chloride produced. So we know the rate that the hydrochloric acid is being consumed. At what rate is the magnesium chloride being produced? So this is a real simple little stoichiometric calculation. So let's rewrite the rate that the hydrochloric acid is being consumed like this. So it'd be 0.30 moles, but now it will be specific. Moles of what? Moles of hydrochloric acid per liter seconds. So that's the rate that the hydrochloric acid is being produced. Then we simply look at the balanced chemical equation that tells us that for every 2 moles of hydrochloric acid that react, we'll make 1 mole of magnesium chloride. And so we simply use a mole ratio. The hydrochloric acid is in the denominator so that we can cancel it out. And that was simply that the liter seconds would remain. So all we do with this step is substitute in magnesium chloride for hydrochloric acid. And so the rate at which magnesium chloride is being produced would be 0.15 moles per liter seconds. So it's just that easy. All you need to do is to write down the rate of a particular reactant or product that you're given, and then use a mole ratio from your balanced chemical equation to convert from the unit that you have, in this case hydrochloric acid, to the unit that you want, in this case magnesium chloride. It's just that simple. Any measurable property that differs between reactant and products can be used to measure the rate of reaction. So I'm going to list, I think, 6 or 7 examples here. So, and all of these are just things that would change as time goes by. So as time goes by, you can measure that change. So let's say a reaction is exothermic. As time goes by, the temperature is going to increase. And so the rate of the reaction could be change in degrees Celsius per unit of time. Absorption of light. So let's say that the reaction produces a cloudy solution and light can't be transmitted through it very easily. So as time goes by, less and less light is going to be able to pass through a solution. Electrical conductivity. Let's say that the reaction produces an electrolyte. So as time goes by, the solution, takes place in solution, will be able to conduct electricity more readily. So you can measure the increase in electrical conductivity as time goes by. Volume of a gas. If it produces a gas, you can measure that gas as it's being produced. A change in pH. If the reaction that we just looked at, magnesium and hydrochloric acid is an acid. It has a low pH. As that reaction progresses, the pH is going to go up as the acid is being consumed. Or we could look at the change in color. Many reactants and products have colors, and so we can monitor the change in color as time goes by. Collision theory states that for a chemical reaction to occur, the reacting particles must collide with one another. And I always remember when I first heard this, it just had never occurred to me. When we write a chemical reaction, we write these reactants right next to each other, with those particles literally need to come into contact with each other. But not just that. I'll refer to this animation in a minute. Specifically, the particles must have sufficient kinetic energy to break bonds. This is called the activation energy. And they must have correct collision geometry or orientation. So the particles here, let me stop this for a second. So the particles are colliding with one another. If they collide with one another with sufficient kinetic energy, then bonds will break. And that's what we mean by activation energy. But it's not just that they need to collide with sufficient energy, but they have to have correct orientation. They need to hit each other in the right way. Okay, so I'm going to show you a little video to review this, to review collision theory.
Here's a beaker of cold water and a beaker of hot water. When you add sugar cubes to them, the one in the hot water will dissolve faster than the one in the cold water. To explain the different rates of reactions, Max Trotz and William Lewis came up with collision theory in the early 1900s. The first assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's needed for a reaction to occur. The particles also need to have enough energy, enough speed, to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy.
Okay, to this diagram that she's showing you, I'll look at this in just a minute.
Some reactions require very little, and some need a lot more to get started. Generally speaking, most reactions will occur faster when the temperature is increased, because temperature is the average kinetic energy of the particles. With more kinetic energy, they will be more likely to have enough activation energy for the reaction to occur. But for some reactions, there is still one more factor: orientation. Even if the particles collide with sufficient speed, if they aren't at the correct angle, a reaction won't happen. In this example of nitrogen monoxide and ozone, the reaction didn't occur because the oxygen of each molecule touched during the collision. In this collision of the same two molecules, the nitrogen touches an oxygen and the reaction occurs, making oxygen and nitrogen dioxide. The orientation was correct, so the reaction could occur. So in summary, the three key ideas of collision theory are that particles must collide to react, they must have sufficient energy to break and make new bonds, and they must collide with the correct orientation.
Okay, so let's look at an example reaction. So it's carbon monoxide reacting with nitrogen dioxide to produce carbon dioxide and nitrogen monoxide. All right, now this diagram I'm going to show you is similar to the reaction that we looked at, I'm sorry, let me start over. This diagram is similar to the endothermic and exothermic diagrams that we looked at early in this unit. But what's new here is this hump. This is called the activation energy. So I would encourage you to copy this diagram down. These are some key parts. Activation energy. Now I'll give you a definition of activation energy in the next slide. So the reactants, recall, have a certain amount of energy. The products have a certain amount of energy. This would be an exothermic reaction. The reactants have more energy than the products, and so the products minus the reactants will give you a negative value. And so this is an exothermic reaction. But what we didn't look at before is this additional energy that's necessary for the reaction to take place. So, like we said earlier, the reactants literally need to collide with one another. Okay. So carbon monoxide and nitrogen dioxide literally need to collide with one another. But they need to collide with each other with sufficient energy, and that's called the activation energy. Now, a real good analogy for this is imagine you're rolling a ball up a hill. Now, in order for the ball to get over the hill to the other side, you have to supply it with sufficient energy. You need to throw it hard enough for that to occur. Now, sometimes you might be able to throw it, or you might throw it hard enough for it to roll up the hill, but it just doesn't quite make it over and it comes back. But in order to make it over that hill, we have to give it sufficient energy, and in chemistry we call that the activation energy. And it's literally just the kinetic energy of the collision between the particles, the speed of the particles colliding with one another. Now, when the particles collide with one another, for an instant, they are merged together as one, and that's called an activated complex. And in a subsequent slide, I'll give you a definition of activated complex. But it's just like it looks here. These two particles are colliding with one another, and for a brief instant, they are one. Now, they may have sufficient kinetic energy to make it over to the other side to form products, or they might just break back to what they were and form the reactants once again. That would be the case of like the ball rolling up the hill and not quite making it over and just coming back. But if the collision is successful, then we form products. All right, so let me give you a couple of definitions here on activation energy and activated complex. Okay. The activation energy, capital E sub A, the minimum amount of energy that particles must possess in order to break bonds. And so this is the additional energy that the reactants would need for the reaction to take place. Remember when we first looked at this a few weeks ago, we just went from the reactants down to the products. And so this was a missing component there, this additional energy that they need to have. And it's literally just the kinetic energy of the particles moving and hitting one another. So now let's look at activated complex. It's also referred to as a transition state. A short-lived, unstable arrangement of atoms that may form products or break apart to reform reactants. So the activated complex is this here. It's literally the two reactants merged together as one in one brief moment of time. But like I said, like it says here, it may form products or break apart to reform the reactant. So like I said earlier, that would be the case of like the ball rolling up the hill, but not quite making it over, and this just coming back down to reform the reactants. But with sufficient activation energy, it will form products. Factors that can affect reaction rates: temperature, concentration, and particle size. Now, for particle size, it would just be for solids. Now, we'll have examples of these in just a minute. But let's look at what we mean by particle size of solids. The smaller the particles of a solid, the greater its overall surface area. So imagine that you have a solid and you break it into pieces and then you break it into more pieces. Well, the smaller the pieces, the more surface area. Surface area increases as the particles get smaller and smaller and smaller. All right, let's look at an example reaction. Solid calcium carbonate reacting with hydrochloric acid to produce calcium chloride, carbon dioxide, and water. Now what we're going to do is we're going to monitor the rate of the production of carbon dioxide gas and see how three different factors affect it. First, we'll look at the effect of temperature. Then we'll look at the effect of changing the concentration of the hydrochloric acid. And then we'll look at the effect of changing the particle size of calcium carbonate. Let's first look at temperature, the effect of temperature. Now, the plot that you're looking at here is the volume of carbon dioxide gas versus time as time goes by. And for each one of these variations, you'll see two plots representing two different variations of a particular condition. So this line represents the lower temperature, and this line represents a higher temperature. Okay, now let's just pick an arbitrary time t, draw a line for that time, and we can see that at that time, the higher temperature is able to produce more carbon dioxide gas than the lower temperature. Rate increases at higher temperature. Now, in the next slide, I'll give you a rationale for that. But what's important here, well, that's important, but what you need to be able to do is to differentiate between the two curves. If I was to give you a plot of a particular chemical reaction with two curves and say one represents a high temperature, one represents a low temperature, you need to be able to label which one's which. And it'll always be, for our purposes, it'll always be that the higher temperature produces more of a product than a lower temperature. Now, I should point out here, notice that they both plateau at the same place, and that just means that it doesn't matter the rate of the reaction. Eventually, you're going to run out of one of the reactants. So as soon as one of the reactants is gone, the reaction is just going to stop. But the higher temperature here, you can see that we arrived at that point much faster than the lower temperature. Okay, now the rationale for the higher temperature. An increase in temperature increases the collision and the effectiveness of those collisions. Okay, now let's look at the effect of concentration. It'll be the concentration of hydrochloric acid, so we're changing that. But again, it's still the volume of carbon dioxide gas that we're looking at as time goes by. So again, let's pick time t, draw a line to represent that, and we can see that at the higher concentration, we produce more carbon dioxide gas than at the lower concentration. So rate increases at greater concentrations. An increase in concentration increases the number of collisions. Greater concentration, the more moles, the more particles, the more collisions. Calcium, sorry, the effect of surface area. All right, so now we're looking at the solid calcium carbonate. So we have powdered calcium carbonate, and so that would be greater surface area. Powdered means that we have very, very small particles. Remember we talked about earlier, the smaller the particles, the greater the surface area. Whereas large pieces would have a low surface area. So you can see the powdered, this at the time t, produces more carbon dioxide gas than the larger pieces. So if you wanted something to react more quickly, you would grind it up to smaller pieces. So rate increases with greater surface area. Now, kids often get kind of confused with this because the larger pieces is the smaller surface area. The smaller the pieces, the greater the surface area. So an increase in surface area increases the number of collisions. Okay, that's it for introduction into kinetics. A little bit more, not too much more next week on this, but that's the end of today's notes.